probability in lots and lots and lots of different capacities, okay? So as we think through probability, there's a couple of components that I want to make sure we understand. Number one, we don't want like loose answers where we're just writing decimals. We want to make sure we're communicating what we are finding the probability of, okay? And the other thing is that what you guys think you know about probability is, I wouldn't even call it the tip of the iceberg. Okay, there's lots and lots of things we need to know about probability. Most important of those is how to select the appropriate tool to calculate a probability. So I'm going to teach you lots and lots and lots of probability tools. The hard part is not going to be how to use any given one of them, but rather which one and how do you know which one to do? So we're going to be focusing a lot on that. You're going to hear me saying some phrases over and over and over again. My intention is not to be treating you like children, okay? But rather, I emphasize the phrases that will help you pick your tool later on, okay? All right. So we're going to do something called a simulation today. We're going to do a couple simulations, maybe, hopefully, okay? When I was a kid, they used to, you'd go and you'd pick up like a bottle of pop or something and you'd untwist the cap and literally the words, "You are a winner," or "Try again later" appeared in the bottom of the cap. Nowadays, they tend to do like, type this code into your phone to see if you've won this contest, okay? So I want you to imagine that we're playing a game where if you open it up and it says you're a winner, that means you get a free bottle of soda. And if it says try again later or please try again, you don't get the free soda. Cool? And Coca-Cola is saying that the probability of winning is 1 in 6. Everybody good so far? Okay. So if you and 6 friends go into a store, that would be a total of 7 people, yeah? And if that were the case, how many people would we expect to win? Expect 1, maybe 2 winners. Great. And the way you came up with that answer, I'm assuming, is you picked 1/6 of 7 is a little bit more than 1. Is that a fair assessment? Okay. All right, so it turns out that, in fact, not one person, but 3 people won. And the guy behind the counter is like, what? That shouldn't have happened. Would you guys be shocked at 3?
Yes.
Okay, so right now, we're kind of shocked. In fact, you guys are all saying yes. The cynic in me is like, What is the probability?
Oh, that's lucky.
So we say that's lucky that it happened. What's the probability that it would happen? And you get 3 people who won. Nope.
It's the same as 1/6. Is it like 1/6 to the 3rd?
Okay, so here's the 1/6 to the 3rd would be the probability that 3 out of 3 people could win, right?
Yeah.
But like when we think about it, let's just say that it's you 3. 3 out of 3 would be 1/6 times 1/6 times 1/6. But the minute I include Sylvie, and there's 4, now there's 4 different ways you could get 3 out of the 4 of you to win. Do you guys get what I'm saying? When you add in more people, there's more ways for it to happen, period. Is this okay?
Yeah.
All right? And so all of a sudden we kind of have to count in like all the different ways we could pick 3 of these 7 people to win. And then we got to think through, like, if that's the case, you don't just have the 3 winners, you have the 4 losers. So it gets really hairy really fast. Do you guys get what I'm saying? Okay. So, man. So the probability we need to find is the probability of 3 winners. Given 7 attempts. Which is different than just saying getting 3 wins. Everybody good? Okay. So, when I said we have to be kind of like particular about what probability are we finding, like we gotta be a whole lot more descriptive than we're trying to find 3. The probability of 3. Because probability of 3 if there's 7 people versus the probability of 3 if there's 100 people is also quite different, right? Okay. Now, so essentially we kind of have 2 hypotheses that we're going to kind of explore here, sort of. Okay? What are 2 ways to explain why we had 3 winners?
People got the 1 in 6 chance to win.
Just so that essentially luck, right? And so one explanation is that the probability actually is 1/6, and this group of people got lucky. The other explanation?
The odds are not correct.
It's rigged. And in fact, ours suggests it might be bigger than 1/6. Is everybody good? So we're trying to make the distinction between these 2 things. All right. Now, we are going to start off the next unit with the actual way to calculate this, okay? And instead what we're going to do today is come up with a decent estimate for this instead of like trying to do all the calculation. You're not ready for that yet, okay? So, how could we simulate a 1 in 6 chance? Huh. So if I rolled this die, and we're going to say that if you roll a 1, you 1. You see what I did there? It's pretty punny. Okay. All right. So I'm going to roll the die, and Sylvie, did I win?
No.
What's the probability I win? I didn't? That's impossible. I did it twice. It's 50-50. Just kidding. Oh boy.
You didn't win.
I still didn't win. Okay. So every time I roll the die, what is that simulating? 1 attempt. Opening 1 can of soda. Yeah? How many are we opening?
7.
So if I roll 7 dice. You guys with me? I think I'm gonna make a mess, don't you? I'm slightly worried about, I'm not really worried about it getting all over the floor other than rolling under the cabinet.
Yeah.
So I'm gonna be like a hockey goalie.
Just go on that table.
Or just go.
Oh! I did not think you would do that.
Two ones, I think. You won.
I won twice. 2 people won in this particular case.
Yes.
Everybody good?
Yeah.
Okay, so here's what we're going to do. Each of us is going to do this 10 times. So I'm going to hand each of you a stack of 7 die. I want you to start a dot plot. So for example, if Ms. Meister was starting her dot plot, I would put a dot on 2 because on that particular turn I had 2 winners. This time I have 0 winners, but a pretty decent Yahtzee roll. You guys get the basic gist of this? Okay. So, like I said, I will bring around stacks of die for you. Start recording until you have 10 dots on your dot clock, please. I sure didn't. Okay, so now we have the combined, right? So if I said, what is the, with 122 dots, I said to you, what is the probability of getting 4 out of 7 people to win, according to our simulation? 1 out of the 122 dots that happen to be there, yeah? Now, I'm going to change the way I phrase that question. It means the exact same thing. Instead, I said according to our simulation, but essentially what this means is the probability of getting 4 winners if that original claimed probability is correct. If the probability of doing it by luck is 1 out of 122. Is everybody good? Okay, because when we did this, we assumed that 1/6 was true. Okay. All right. What's the probability of getting 3 or more winners? What would we need to do? We would essentially need to count how many of those 122 trials are 3 or more. 1, 2, 3, 4, 5, 6, 7, 8, 9, 10, 11, 12, 13. 13 out of 122 times. Leaving that probability to be about 10%. In fact, it's 11%. You guys, could it have happened by chance? Do you think they're lucky? Would you call 10% unlikely to happen by chance?
Yeah.
I wouldn't call it likely, but I wouldn't call it I would call it reasonably likely. Like, it could happen. So, we talked about in the last unit, if we have an experiment, or when we talked about Lady Adeline, it's different from what we would expect. And the question is, how likely is it that we would see such a big difference from what we'd expect? There's a 10% chance it could happen by chance alone. To me, that is not super unlikely. That's slightly more than 1 in 10 chance of it happening. Not that crazy.
What would be super unlikely?
Yeah, of course you're going to ask that question because you want a rule to follow. Typical rule of thumb is 5%. But in reality, man, does it depend on a lot of different things. But you're for right now, the unlikely to happen by chance, unless I tell you otherwise, we're going to use 5% as our kind of like something in right.
So it would be unlikely to be rigged.
Oh boy. I would say we do not have enough evidence to say that it is rigged. I would not say it's unlikely to be. That's a lovely question. I want you to know how lovely your question was and how impossible it is to answer right this second, because we will get to it this year, I promise. The wording of, there's a big difference between saying it could occur by chance and saying it's unlikely that it's rigged. There's like leaps and bounds differences between those two things, and to just, yeah. Okay? I know that didn't answer what you wanted it to answer, but you guys, could we do rolling a die on our calculator?
Random number.
Yeah. What if I just did a random integer between 1 and 6? Would that have worked? Could I? And in fact, we talked about these, right? We did these and I could do between 1 and 6, and let's go ahead and do 7 numbers. And now, boom, in this case, the person won twice, yeah? Or 2 people won. Each of these numbers would be a person opening a soda, yeah? Here, it's 2 winners, 1 winner, 1 winner, no winners, no winners, 1 winner. You guys with me? So it's all right. So there was a question on an AP test. I can't remember what year it was. It was early. It was like 2012. And it was a question where you had to calculate a probability, and the students didn't know how to do it. A few kids, not many, set up a simulation like this and got credit for it because they ran the simulation, which is actually pretty sweet. Okay. For right now, let's talk what we need to do in order to set up a simulation. Because your calculator has that random digit generator, you can roll a however many sided die you need to. Is everybody with me? Okay. So the things that you would need to say is, 1, how are you going to ensure it's random? Using a random number generator does that. And you got to make sure you're setting it up in such a way that initial probabilities match what they're supposed to, and that you know what you are recording. So we're going to run a quick simulation to talk about, to come up with an estimation of the probabilities if someone is an 80% free throw shooter and they take 5 shots. Everybody good? All right. Now, the question we need to answer is, how many makes out of 5 for an 80% shooter? All right. So, first things first, we got to model a shot for an 80% shooter. Everybody good? So here's what I need to do. I'm going to use a random digit generator because I think it's easy. Let's go ahead and let 1 through 8 be a make. 9 and 10 be a miss. Is that going to be that they make it 80% of the time? Could I have done 1 through 4 and then 5? Yeah. Could I have done 1 through 80 and then 81 through 100? Are you guys all with me? Okay. All right. So here's what I'm going to do. math, arrow over to PRB on the top. It should be option 5, I think. Okay, so for me in this case, you guys, how many did he make?
4.
4. And how do I know that?
Because 4 of them are below 9.
4 of them are between 1 and 8. Okay, so here's what we just did. Use a random number generator to get 5 numbers. In this case, do they have to be unique? Nope, because they don't represent individual people. Okay? So the numbers we generated were between 1 and 10, and we're counting the number of values between 1 and 8 because they are the makes. And so in this case, we had 4 makes. I could do it again. In this case, we have another 4 makes. Because when I did these ones, 4 of them were between 1 and 8. Man, this is a very consistent shooter, huh? You guys get the general premise of where this is coming from? All right. We started with what is the question we're trying to answer. We created a trial in such a way that it had the correct probability that we were trying to model. And we recorded it so that those probabilities held. Is everybody good? We're paying attention not to just what we did, but also what we're recording at the end. Is everybody good? Okay. All right. So let's say I went ahead and did this a bunch of times. I don't know, like 25. According to this, what is the probability of getting 3 or more shots? A reminder? I did this so that it was 25 times. Now, those of you who are saying 22, that is not my probability. My probability is 22 out of
25.
And when you guys said 22 out of 25, how many of you counted all the dots? Sometimes it's easier to count what's not there versus what is there. Yeah? Guys, that's 88%. So according to this simulation, the probability that this kid's going to make 3 or more shots is 88%. That's how we might read that. Okay? All right, now, if you turn the page, we got 3 more simulations. For each of these, what is the probability that x is greater than or equal to 3? I'm sorry?
Are they all 25 still?
Yes. The first one? Not 0. 100%. 25 out of 25 are greater than or equal to 3. Yeah? For the second one, 24 out of 25. For the third one, 24 out of 25. Are you guys with me that each one of these simulations had a different result? So what's the problem with simulation? It's not even that it's not always, it's definitely an estimate, period. It's an estimate of the probability versus an exact value of the, okay? But most of the time, they're pretty close. And in reality, what we could then do is we had a total of 100 simulations. And if you looked at them all, 95 out of the 100 simulations. So the more simulations we do, the more and more this is going to start resembling the true probability we're trying to get at. We're going to start with a conversation of what is probability. Now, I'm going to ask you guys this question, but before you answer this question, there are a few words you are not allowed to use to describe what probability is.
Probability?
Obviously probability, but the word chance, likelihood, odds. So between probability, chance, likelihood, and odds, you're not allowed to use those words. What is probability?
The randomness of something.
The randomness of something?
How often something happens and the total amount of ways it can happen?
That seems like a good way to calculate probability. But what is it? This feels icky, right? You know how many times I start with what does it mean to say, for instance, this is a 20-sided die. So the probability of rolling a 1 on this is 1 in 20. It didn't happen. See? Okay. And I'll say, well, what does it mean for something to have a probability of 0.05? And students will say, well, that means the odds are 0.05, which technically is not true. The odds are 1 to 19. But, or they'll say that's the likelihood. And then I say, what does likelihood mean? You know what they say? Probability. It's the probability something happens. We use the words chance, likelihood, and probability interchangeably, but we don't really understand what they mean. Oh my gosh. It wasn't one. It did run into something. 11? Man, all of them have been so close to each other. I wonder what the likelihood of that is. They roll 1? No. What if I roll this one? 100. This is a D100, which was accurately predicted this morning in 4th period. 20.
How does
20.
it stop?
20.
Does it ever stop rolling?
It does eventually stop, but it takes a while. Like, I'm going to keep lecturing while we wait for it to stop.
Where did it go?
It's not. Oh, it's a 1.
It's a 1.
It is a 1.
But the 1 is bigger than all of them.
Technically,
You guys get perfectly know?
the 100 is, right? Because that's the side that was on the bottom. Do you think it'll be a 1 again?
Yes. 100%. It's a 50-50 chance.
I'm about to kick you out of class. So, if I asked you to define any of these words, right now are we feeling a little bit icky about trying to come up with an explanation of what those words actually mean?
Yeah.
Okay. All right. So, here's what we're going to do, a nice little thought experiment. We are going to roll some different sided dice. I have all sorts. You know you can order a pound of dice from Amazon? So I have so many good dice here. I have a 4-sided. Has anybody ever seen a 4-sided die before? So with a 4-sided die to roll it, that came up 3. It's actually the point at the top, so it's not the sides that have numbers, but it's the vertices. think that one's cool. I got the D8. Oh. D20. I got the D10, D12. You guys get the D12? And here's what we're going to do. Sylvia, I'm going to have you pop back with Sophia here. Okay? You guys. In probability, we have events. We're in probability models. We have events and we have outcomes. So an event is a chance process. And an outcome is a possible result of said chance process. Okay, so here's how we are going to define our event. Our event is going to be a roll of a dice. Everybody's got, you guys each have different ones, yeah? All right, so in that roll of the dice, the way we are going to define our outcomes, we can define them lots of different ways, right? It could be, for instance, in this 8-sided one, it could be one outcome is a 1, one outcome is a 2, one outcome is a 3, right? But couldn't I define these outcomes as odd or even? Sure. This one was an odd. This one was an even. Yesterday we defined 1 as winning and not 1 is losing. You guys with me? So a chance process has different outcomes depending on what we're looking to do with that chance process. Okay. The outcomes we're interested in this particular chance process that I'm going to have you guys do are 1 and not 1. Now, whose dice has the highest probability of being a 1, or which of the dice? We had a D4, right? Okay, and we have a D8. That one, right? We have a D12 or a D10, D12, D20. Did I give anybody a D6? You get the D6, okay? All right. And are you guys with me? Highest probability of rolling a 1, lowest probability of rolling 1. Okay. So to explore what does it really mean to say something has a probability, what we're going to do is do some rolling. So at tables, whatever, I want you guys keeping track. I want you to do at least 50 rolls.
Of keeping track of how many are ones and how many are not ones.
1 versus not 1, 50 rolls.
You'll keep track of all these. Okay. So one's gonna have
No. 6. Sorry? No. 1. No. 11. 6. Okay, well, I'm gonna need 2. 7. No. 1.
Wait, no, 5.
I'm not even didn't do it.
Wait, what is it?
The Fibonacci spiral. The Fibonacci sequence goes
So still 2 out of 50.
So what?
Okay.
11 now out of 50. Yeah, that's what I have. It's a
So you
famous
just add whatever the ones.
the previous 2. And so
No, there's just 7.7% chance I just don't get 1.
1 inch square, 1 inch square, 2 inch square, 5 inch, 3 inch square, 5 inch square. That's a very famous pattern. Like if you
Yeah, but
take it out as far as you can, which you can't because it can go on forever. But like, so 2 over 1, 3 over 2, 5 over 3, 8 over 5,
my old squad, like my 260 pounds.
etc. That approximates a number called 5. 5.
I brought some more.
Like 5, what was
My
that?
dad threw it a couple times on one.
Like 5 with what would change because it's Greek. There's no F in Greek. This is the Greek F. This is the Greek F.
It's also very similar to in Russian. It's really
These, this spiral
At one point, I was
is the
15
same
pounds.
spiral that
Yeah.
like shells that are spiral and
It's like why?
it's so it's more of a someone noticed that it happens. And if you look at like so 5 is what we call the golden ratio. Like if I were to ask somebody to draw me a rectangle, it is very likely they draw that rectangle in such a way that if this is 1, this is 5. Like it's a ratio of rectangles basically. And like in architecture it shows up a lot. Like if you look at like the Parthenon and all those kinds of things, like they all go at this ratio. If you look in nature, the Fibonacci numbers, like the number of petals on different types of flowers, are quite frequently Fibonacci numbers, as are in the pine cones and all that kind of stuff. You know, you can look in that, or like in a sunflower, you can start to see a spiral. It's the spiral. It's exactly what it is. All right, you guys have the D4?
Yeah.
How often out of 50 times did you guys get a 1?
11.
11 out of 50 times. Okay, and then D6, how many times did you get a 1?
7.
Got it in the D8 group?
3.
3? D10?
2.
D12?
5.
5? Okay. So I'm going to call that 1. Bzz, okay. So with one anomaly, are you guys with me? That what happened as we had those lower probabilities is the frequency of what occurs decreased. And if we did this 100 more times, I'm not going to make you do it 100 more times. These almost go down together, yeah? Right, like if we did this 100 more times, this group is, you guys aren't going to have as many, right? Like it'll even itself out. Okay, so But what if we all rolled it one more time? Do we have any idea what's going to happen on that one roll? Like if I could take this one right now, do I know what's going to happen? If I roll it one time, I got no idea. If I roll it 1,000 times, do I have a pretty good idea of what I'm going to get? Did you guys get what I'm saying? Okay. So, chance behavior is unpredictable in the short run and very predictable in the long run. Now, for any one of these dice, could I ask you guys to find the probability of an outcome? Like this 8-sided dice, what's the probability I get an even number? 50-50, yeah. 4 out of 8, yeah. What's the probability I get a number that is less than 3? 2 out of 8. So calculating probability, and like simple probabilities is not something I intend to teach you. You're not going to get a problem that says, I have a bag with 5 red marbles, 3 white marbles, and 2 blue marbles. What's the probability you draw out of blue? You would get so bored if that's the kind of problems I would give you guys. If I gave you guys, let's put it this way. What if all I had you do was flip dice all day today? Would you have gotten annoyed with me?
Yes.
Based off of these numbers, could we estimate the probability for each dice?
Yeah.
More or less. And what would it be? So, like, if I asked you what is the probability of, say, this dice, I'm picking it because the numbers are lovely. 1 in 10 or 10%, yeah? And that was the D12, so we were hoping this one would be 1 in 10, but we get the basic idea, yeah? Okay. And if we did it more, we'd get more and more precise as we do our answer. Is everybody good? Okay. So the question of what is probability?